So in the space of automorphic forms of type J theta, and so recall that I said one had this z greater than 0, right? Which was basically you take the center of G and look at the points of Z, the A greater than 0, the A cross greater than 0 points. So maybe I should remind you what this is. So we have this consists of all things of the form. So this will be an Adele, and it will look like, say, T, T, 3, and then 1. Right, all such things. So X in the Adeles with this. Wrong order, but X and Adele. So here these are the infinite places. So it's going to be the same thing at the infinite places, and at all the finite places it's going to be 1. Okay. So and this is again just going to be scalars. So it's just going to, I can just identify it in fact with some X like that. Okay. So what I said yesterday was essentially whenever convenient, so I will just do this without comment, but whenever convenient, we'll assume my automorphic form phi zg equals phi of g. So this is the last thing I did for all Z greater than 0. Okay. So I mean, as I said yesterday, you have ZA finiteness anyway, and then you can basically therefore write everything as a linear combination. Essentially, after scaling by some factor of determinant, you can write everything as a linear combination of such things. So whenever I need to, I will just assume it is Z greater than 0 finite. Okay. So let me first maybe state a lemma. Yeah. Okay, so here's a lemma of Harishchandra, which we will need. So select phi 1. So this is actually for just okay. So phi 1 phi r be k infinity finite and zg finite functions on G CC in CC infinity or G infinity. So this is all happening only at the real at the Archimedean places. Okay. Then sorry, not. Yeah, ZG finite functions and functions on G infinity, right? Then there exists f in CC infinity G, such that phi convolution f equals phi I convolution f equals phi I for 1 less. Okay. So this will be a useful lemma. We see that quite often, both to prove. So sorry. Phi is phi I. I have a family of functions. I mean, I have R functions, and I have phi convolution f equals phi. Yeah. In fact, you can take f to have support in any neighborhood U of the identity, but that won't be important in what follows. Okay. All right. So this is a useful thing. In fact, let me make a couple of remarks. So, essentially, this is a much more general lemma which we won't use, but anyway, I thought one should state due to things being. Malima says the following, right? That if I have any, so if I start, let's take a unitary representation of. So over here I'm working entirely with G infinity now. Okay. In fact, I can take groups that are products of more generally. So G infinity was some product of GLNRs and GLNCs, and that's what I'm looking at. Okay. So this will be in general products of GLNRs and GLNCs. Right? So I'm looking at such things. This is not an adelic statement right now, this is entirely an Archimedean statement. Okay. So suppose I have a representation, pi h, unitary representation of G infinity on a Hilbert space. Okay. Maybe I should put this before the statement of the lemma, but anyway. So I can look at V, let V be the space of C infinity vectors, smooth vectors in H, right? And then on this, one can topologize this using a family of semi-norms. So you have the semi-norms roughly given by V goes to say pi x V. So this is the Hilbert space now, and I can vary x in the universal enveloping algebra, right? So this gives me a family of semi-norms, and essentially it turns out that this space is complete with respect to this family of semi-norms, right? So V is complete with respect to these family of semi-norms, and the lemma actually is going to say that if I have any smooth vector, so for any V in V, if there exists Fi, what do I call them? Yeah, Fj, okay. Right, so I can always write, there exists Fj in C infinity, A infinity, and Vj V, such that V can be written as the image of pi of j. I mean, it can be written as a linear combination of the pi of j. Alright. So this is a more, as you can see, this in some sense, it's not exactly this, but it's a slightly more general statement. This is for C infinity functions with a regular representation, and there I have something more generally for smooth vectors in a unitary representation. Okay, so just another remark, maybe. So because of this lemma of Harishchandra, right, and the following statements, so I think this is something Arvind asked yesterday. So so you see, you have the uniform, you have that moderate growth condition. So the moderate growth condition was the following statement. Right. Was a statement that whatever G is less than or equal to, say, some constant times norm G to the M, for some constant C in greater than 0, while G in GA. Right? So sometimes people demand moderate growth not just for phi G but for all X phi, where X is in the universal enveloping algebra. But essentially, because of this lemma, it amounts to the same thing. Because since we have phi convolution. Okay, so this is actually maybe I should make this comment after pointing out the corollary of this lemma. So this is an Archimedean lemma. I will make the corresponding statement for adelic functions. So let me just write that and then So before this remark will be completed after the following lemma.
Maybe it must have some property, otherwise it would be.
No, I'm saying where?
Just because norm phi is bounded, the derivatives of norm also are bounded, must need some hypothesis.
Yeah. So that's what I'm going to make it. Now, this phi is an automorphic form. So just remember that moderate growth condition. If phi is an automorphic form, it satisfies this. And then I'm just saying that automatically. So let me make the statement, right? So first, if phi is an automorphic form. So just remember. So maybe this is not remark yet. This is recall. This is what the moderate growth condition means. If phi is an automorphic form, right? So this is almost immediate from Harishandra's lemma. There is an f, just the adelic version of that, CC infinity GA, such that I convolution f equals phi. Okay. And so now the two-line proof will just be, of course it's true at the Archimedean places, so you just want to extend the function suitably to the finite adels. That's all there is to it. So if we take, remember that because of weak approximation, we have GA equals a disjoint union of GF. So I equals 1 through K of GF, G infinity, Gi and K prime, right? For any compact open subgroup K prime of Kf, right? And therefore, I can simply take my phi I G infinity to be phi G infinity. Let me call this Ci. Ci. Remember this here Ci were in GF. Okay? So if I take the phi I G infinity to be just phi G infinity Ci, right? Then lemma 1 says, right, I can find there exists f in CC infinity such that phi I convolution f equals phi I, right? And so now I can simply define, say, a new f, which you have to do G infinity GF. I simply define this on the adels to be, this is just some obvious normalizing factor to get the whole thing back. F infinity of G infinity. So let's call this, there exists F infinity. If G is in K prime and 0 otherwise. Right? And one checks obviously that this is the F that will do the job. So you simply have the F anyway. So the only point is, you start with a phi, there will be, if I start with a phi, it will be basically be given by some number of phi i's at the Archimedean places, right? And those phi i's, for that collection of phi i's, you can find a single F infinity, so that phi I convolution F infinity is phi I, and then you just extend that F infinity to an F by setting it to be 0 outside the relevant compact subgroup. Okay? So this tells you what you want. So the remark, which I will now complete, I guess, is that, right, for every x in UG, right, x of phi I convolution F is obviously phi I convolution XF. This is just because you can take the partial derivatives inside the integral value of convolution and transfer it to the second factor. So this means that, and in general, that the right translates of phi and phi convolution F. If phi has moderate growth, then automatically the right translates of phi have moderate growth, and therefore the convolution of phi with any compactly supported function is going to have moderate growth. Okay, and now I've simply I've expressed my x of phi convolution F as phi I convolution XF, and this again has compact support. So if the original phi had moderate growth, so yeah, so then so does, right? So hence x convolution x of phi convolution F has moderate growth, and in fact with the same exponent, because when you translate and when you convert with the function of compact support, the exponent remains the same, it doesn't change, right? Because essentially all the you're basically right translating by elements which remain in a compact set, and outside a compact set things don't matter, right? So okay, so x convolution F has x of phi convolution has moderate growth, which is of course nothing but x of that has moderate growth with the same exponents. Okay, so I think this was, so sometimes books will define an automorphic form. The moderate growth condition will be defined, will be stated not just for x5 but for all, not just for phi but for all x5. But in fact, it's equivalent because of this limit. Alright. So I think this was Arvind's comment yesterday, or question yesterday, and that's okay. So I can erase this, or yes.
There are lectures of Narayanan.
Yeah.
Somebody had asked and he had responded that the difference between C infinity vectors and body space.
Yes. Huh?
Here,
The Dixmedia Malima says essentially they're the same thing. Yeah, they are. Yeah.
So,
Indeed.
he said that there is a counterexample, and in fact I was a bit concerned there. Narayanan is there, no?
Yeah, these are more precise statements about factorization.
Which? Dixmedia Malima? Yeah.
Line subspace is just a space of C infinity vectors which is dense.
Yeah, but this kind of tells you they're the same, right? That
No, the consequence is that it's dense, but here you are saying any C infinity vector is, so it's like CC infinity convolving CC
Yes.
infinity is equal to CC infinity.
Yes.
That's
Yeah.
stronger statement than saying it is dense.
okay. Yeah. So I don't know what statement was made exactly, but
No, but he still is saying something.
but anyway, yeah.
You agree with Narayanan that C infinity vectors are same in guiding space? Because you said it's not true.
What is the question?
No, I think you said that C infinity vectors in the representation are not the same as the guiding space.
Yeah, they are not.
They are not. You see?
Okay, well, okay, maybe I don't want, let me not get into this now, but
No, I really give you as he said.
but guarding space is what for you? I mean,
You
it's,
said pi of D.
right. Okay.
Yeah, well, guiding space is just one term in the linear combination.
One term.
One term.
So it's just pi
But
f.
no, it has to be the span of those things, no? It can't just be one term.
No, it's just pi f. The
Span of
Oh, well, if you take the span, then.
Yeah, span, no, so it must be the same.
Okay.
Yeah. No, that's what. I mean, the space has got to be in the, yeah, okay. So maybe there's some issue between span versus
Yeah.
one function or something, I don't know. But they are the same, yeah.
Is this something to do with so-called commandment density theorem?
I don't think one.
By commandment being.
You mean, are you asking for the proof of Dixmedia Malima? No.
But there is a very arbitrary representation.
There's the so-called commandment density theorem.
Yeah.
It says that under certain circumstances, if you have a algebra of operators and take the y complement,
Yeah.
then the original algebra is
weakly dense
in that.
the bicomponent. And this seems to be more or less saying the same thing. Anyway.
Yeah, okay, anyway, I should go on, but yeah. Okay, so, yeah, now I forget what I was doing. I don't think I'm going to get anywhere, but let's see. Okay. Alright, so if I, you have to make some difficult choices now.
Here in this definition, you are saying that pattern G, not
Sorry?
what is that G? So F G will be.
Oh, yeah, G. Sorry. Thanks. Point is, you have a function defined at the Archimedean places, you just want to extend it to everything, so you have to say what it is at the finite headers. It's basically the same function, modulo some factor, which when you integrate, anyway, you will get that volume k prime up, so it will cancel with this. So it's just introduced for that.
The volume term is just for normalizing.
Yeah, it's just for normalizing, nothing. That's what. When you do the convolution, a volume of k prime will pop up in the numerator, it will cancel. That's all. Okay, so let's. So inside this now we want the space of cusp forms. So let's remember what they are, right? So if I have a function, so let's do it this way. Alright, so I have a continuous function. So if I could do this with N2 also, I guess, but anyway, it's continuous, right? We will say that. So this has come up in, of course, already, that phi is cuspidal. Okay, so of course, what has to be reasonable function for these things to make sense. So, but okay, let's just assume. So soon we move to L2 if the integral phi in G dn n a by nf. So na by nf is of course going to be a compact group. It's going to be a unipotent group. So I mean n is a unipotent group. This is 0 for the unipotent radical n of every proper any proper parabolic equal to mn of G and for all G. Okay, alright. So this is what it means to be a cuspidal thing. So now we will. So suppose phi. So remember, I can think of phi as being z greater than 0 invariant. Oh, I should probably point out a couple of things. Namely that, so notice that we had, I don't know if I defined G1A last time, but certainly it was defined in Sandeep's lecture, right? So we have, recall, GA equals z greater than 0 and G1A. In this particular case, there it was defined as the intersection of the kernel of some characters and so on, but here in this particular case, since we are in the GNN situation, this G1A, I just got a G1, not G1A. So this G1 will be simply defined as G in GA such that the determinant of G is a unit. So determinant of G okay. So we have to, and the point is, and I think that was said in the last lecture, that if you take G1 by GF, that has finite measure. Invariant measure, of course. So so G1 is also unimodular, GF is whatever. So anyway, so there's no problem here. So we can ask. So the point is, if I look at L2 of z greater than 0 or GF if I look at this space, right, that's basically the same thing as L2 of GF by, so G1 by GF. Okay. So now, so I'm going to kind of freely confuse those two whenever I feel like doing so. Okay. So, I mean, there are some choices to be made, but maybe they're just do the following. That if, so I'll say that phi in, so phi in L2 of cuspidal, if say you do it like this, phi convolution F is cuspidal for all F in CCG. Okay. So now, so I mean, I don't have to bother about L2 and so on because again, phi convolution F is going to be a nice function, continuous, so I don't have to worry about that. So what I want to say is, so I can now talk about cusp forms, right? So I can look at, can look at cuspidal functions in, for instance, A, J, theta, right? And they will be called, so this space will be called the space of cusp forms. Let's say A naught. Okay, so so the first thing we would like to prove, I don't know how far, which I will do in the next lecture though. Okay, so we would like to prove that the space of cusp forms is finite dimensional, so we will prove that. So, lemma, okay, this is the main theorem. Most of our energy will probably go towards proving this. That if phi is a cusp form, phi is bounded. One, in fact, hence phi is in fact in N2, right? So N2 of G. Okay. So remember this has finite measure, so there's once it's bounded. Okay. So recall now. So then further. So now remember we have a strategy for proving that A naught J theta is finite dimensional is in place because we just have to prove that phi is bounded, so that A naught J theta will consist of bounded functions. Of course, I still have to prove that A naught J theta is a closed subspace of L2, and once I have that, then Goldman's lemma takes over. Okay, so that's what I need to prove. Okay, So this is what we'll try to prove, probably make some attempts at proof in the next lecture, as I now realize I'm getting more and more pessimistic about this. So let me first tell you, assume this, and then see why a closed subspace. Okay. So this is just I'm just going to say some words. A closed subspace of L2. So, why is that? Well, not sorry, yeah. So,
Can you recall what are those two objects, J and theta?
sure. So, this is the type of the automorphic form. So, J is an ideal of closed of a finite codimension in ZG, and theta is a finite set of representations of K, and K is K infinity times Kf. Yeah. So we are looking at those objects and trying to prove. So one wants to prove that AJ theta is finite dimensional, but one will start by proving A naught J theta is finite dimensional, and then there is an inductive argument which allows on the rank essentially which allows you to go to AJ theta. I don't think I have any time to get to the inductive argument anyway, but anyway there it is. Sorry? Universal enveloping algebra. Yeah. Yeah. What did I say? No. Also ZG. J is ZG is my notation, right? Z of UG. Sorry. So I mean, yeah. But I've been using ZG for that. But so it's an idea of finite coordinate. Okay. So I have to say the closed subspace of L2, and I'll just say the following: that if phi n, is in A naught J theta, and phi n goes to phi in L2. Yeah, then phi n goes to phi as a distribution, and remember these phi n's, you see they're at A naught J theta, which means they're annihilated by some elliptic operator. It's the same elliptic operator for all the phi n's, okay? And so, and this is an elliptic operator with C infinity coefficients, which means therefore, although phi, so this means phi is a distribution anyway, because phi n goes to phi as a distribution. So hence, as distributions. But the point is, if I have a distribution, so the phi will satisfy the same elliptic operator with C infinity coefficients as the phi n, and once that happens, phi must be a C infinity function itself, right? So therefore, phi will indeed lie this. There's a little more work to be done. I have to say that, of course, there's a K finiteness and J finiteness, but that will also follow relatively easily. Okay, and yeah, and the moderate growth condition likewise will be taken care of. But the main point is to note that phi is actually a function, smooth function, because it's a limit of the phi n's in the distribution sense, and then I guess it's a regularity theorem for elliptic differential operators, which says that if I have a distribution, which is a solution of an elliptic operator with C infinity coefficients, then the distribution is a C infinity function. Okay, so this is why it's a closed subspace, and then once it's a closed subspace, once we prove this, we're done. Okay. All right. So maybe just for elliptic, so annihilated by elliptic operator with C infinity coefficients. Hence, phi is a C infinity function. And then, as I said, you still have to check the relevant G finiteness, K finiteness, but that follows. Essentially, I guess it can be I can, I guess, take theta to be a single irreducible representation, and then this will be the quotient of that or something like that. Let me not say more about this. Make one more comment, which maybe is also necessary. Yeah. So in the same way, let's state, so this is like theorem 3, and then let me also state theorem 3 prime, which is proved by very similar methods, and maybe I'll have a few minutes to indicate, right? So if f is in CC infinity, G and phi is in L2 cusp. So this is the obvious, these are cuspidal functions in L2 as defined before, Gf by G1, right? Then phi convolution F is a bounded and of course continuous function. It's a bounded continuous function. In fact, it's what we call a rapidly decreasing function, but we don't need it. Okay? So what this says is, if I convolve with F, my setup is the following. We have the hence convolution with F gives an operator, hence get on G1, sorry, yes, on G1.
Belongs to the customer.
Sorry?
You already used that it belongs to the customer.
I already used, no. No, by the way, notice phi is now in L2 cusp. Here I started with the
Top of the board.
top of the board. What do I have? No. Yeah, if phi convolute, that's my definition of cuspid.
It's not this and that the same.
No. Yeah, it is, but I'm saying it's a bounded continuous function
Okay, so
on GF. No, see, here I'm trying to make a statement about cusp forms which are in A naught theta j.
top of the previous board.
Top of the previous board is simply my definition of what it means for a function to be cuspid, if you like. I mean, it means that take the convolution and it must satisfy the integral phi convolution of n g dn equals 0. Okay. I'm just doing it so that I don't have to say L2, but okay. I could have said almost everywhere and then that would have come out to the same. Okay. I don't know. So,
No, this is quite elegant.
sorry?
It is elegant to use it this way.
Okay. Yeah. So, hence, our situation is the following: get a. Okay. In fact, we can do better. So actually, I should make a slightly stronger statement because I think I can. Yeah. So in fact, we get the following situation. Hence, we get an operator, right? T. So and of course, by the way, so it of course convolution satisfies the following property. So obviously, norm of the convolution F infinity, I guess, should be less than the 2 norm. Yeah, for some. Okay, so it's not just any operator; it's a bounded operator. So what we have is hence. Right? Get a bounded operator. T from L2. So, more general setup, X is in fact any locally compact out of space, locally compact space, sigma finite, I think, and then maybe I need a dense with a dense substrate. Countable dense substrate. But anyway. So from here, I get a map to bounded functions, CDX, bounded continuous functions. Right? That's what I have. And when you do this, such a thing is necessarily arises as what we call a Hilbert-Schmidt operator. In fact, it arises in the following way. So such an operator. So necessarily is necessarily such an operator is necessarily what we call a Hilbert-Schmidt operator. It's necessarily operator, and such operators, yeah.
It's an operator, X, because what perspective operator? Meaning what?
Imperspective operator meaning it's choose an orthonormal basis and summation.
Yeah, right. That's what it's operator. Delta is to X.
Yeah, CBX,
They're treating it as an operator to X.
L2X, yeah, yes.
So it's a CBX contained inside.
CBX is anyway contained inside L2X.
X is finite question.
And X has finite measure, yeah, that type. Yes, sorry. Good. Okay, so of course, yes, so CBX of course is contained inside L2X because X has finite measure, which is of course our situation. You know, G1 by Gf is the space that we are looking at, right? And therefore, this is what we call a Hilbert-Schmidt operator. If you don't know what that is, it doesn't matter. They're basically, they're compact operators. So if I have time, I'll come back and say something about this. So these are compact operators. Right? But as a corollary, therefore, what we see is since these things come, so essentially a corollary will be that L2 cusp, right, decomposes as a direct sum of irreducible subspaces with finite multiplicity. So this is, I guess, okay. So, by the way, once again struck. I guess, you know, for all Harishchandra knew all of these things, these spaces could be zero at the time when they were proved. One did not know whether the cuspidal spectrum was non-empty or not, except for GL2, and maybe that's pretty much it. Yeah. So when the theory was created, and until, in fact, until the late 70s, people didn't even know whether there existed any cusp forms even on GL3, right? And then, because there is this thing called the symmetric square lift, one in fact knew there were some cusp forms on GL3 starting in 1978 or whatever. So Gelbart and Jacquet succeeded in transferring cusp forms on GL2 to cusp forms on GL3, right? But even those are of course relatively sparse, and so there's something called Weil's law. One expects a certain number of cusp forms counted in a certain way, counted by their eigenvalue of the Laplacian, if you like, up to height b. And Weil's law was known only for the group GL2. So for all we knew, this entire theory was a kind of empty theory. And but now we know it, say, for PGLN in various situations and some other groups. But it's still, I think, an open question. When the Archimedean types are not unramified, I think we still don't know whether they are. This is Lindenstrauss-Venkatesh proved it for PGLN. Lindenstrauss-Venkatesh proved the cuspidal, Weil's law holds for the cuspidal spectrum for PGLN. Okay, but you can get to SLN and GLN also. But they are assuming that the infinity type is unramified. So only for maximal compact subgroups. Yeah. So it's still, I guess there's still. I mean, there was a comment somewhere saying that it can probably be done in general, but given that the two people who wrote the paper never did it afterwards, I'm assuming that, and that they are Lindenstrauss and Venkatesh, I'm assuming that the difficulties are formidable if it can be done. So anyway, so this, by the way, also in general we don't know whether there are cusp forms. Of course, you can by functoriality, we can often lift cusp forms from GLN to classical groups or backward from GLN back to classical groups and so on. So you can get a number of things for classical groups. But yeah, directly. But even there, I don't think Weil's law is known in general. I'm not sure. Maybe functor reality gives Wiles law for classical groups. I don't know. To some extent, I have no idea. But they take G2 or something once or he doesn't know. Okay, so
But what about the uniformity?
Yeah, so I mean, Langham's computed dimensions of space orthogonal forms in discrete series.
this, but that again we rank 1, right?
No, quite well, Basati and all, like that. I think you could, so you knew there were a lot of cusp-forms and groups with discrete series.
But were they sparse in the total set, or I thought there wasn't?
Nothing more than that.
Yeah. Okay. So you knew there were lots, but not. But you couldn't say you didn't have something like Wiles law.
No.
Okay. Yeah. So I stand corrected. So Arvind tells us that yeah, since Langlands computed the space of
In fact, to construct unramified is a hard problem.
Right.
Introduce ramifications and limit multiplities.
then of course you can get yeah.
Easier.
Right.
So the point of ramifications and limit stroke was to do it for that.
No, true, but you still don't.
On SLNZ.
No, I understand, but I don't think you can exhaust everything coming in the when you don't have unramified stuff. I don't think you can exhaust it. I don't think it's been shown that you can exhaust it, but I may be wrong.
But I think for GL, then it's probably what you're saying. I don't know.
For GLN, it's no. Yeah.
No, I mean, it was probably not known
In
in
19 whatever. Yeah. For 1962, it was certainly not known for GLN, I guess. Yeah. Okay. So, alright, but by the way, incidentally, in the case of GLN, so for GLN,
SL2 we know it.
yeah, that's what I said. For SL2 we knew, but that was Selberg.
No, SL2 is you got wrong data.
No, but that's just the holomorphic things, right? But for if you want to say mass forms exist, mass cusp forms exist.
No, but to say that L2 cusp is non-zero.
Non-zero, yeah. But if you want, but those are pretty sparse. If you want to know that L2 cusp is really reasonably large, then again you need to invoke Selberg or something to show the existence of those.
Sorry.
I think the conjecture is Selberg's conjecture was that for non-arithmetic groups you should have Wiles law, and Sarnak's conjecture is that you shouldn't have any. And I think currently Sarnak's conjecture is winning. So there is under Lindelof, blah blah blah, and suitable hypothesis, Grand Riemann hypothesis, etc. You can show some weak statement that basically things. If you deform things slightly, there are no cusp. If you deform your group slightly, there are no cusp forms or something like that. Yeah. So, but I don't know what the status is. So, sorry.
Generically, there will be no response.
Generically, there will be no cusp forms is I think the belief. I don't know. Okay. So, and by the way, incidentally, in this particular case for GLN, in fact, we know that n pi equals 1. This is called the multiplicity 1 theorem of Piotrowski, Shapiro, and Sharika. Alright. Okay, so now, let's see what I can do. Okay, so now we'll go back to some very elementary stuff, but you'll have to go back to Ziegler sets. Okay, so this is what I mentioned yesterday. See, in all of these things, you always have to check this model growth property. If you want to check it, it's kind of annoying to check it on GLN-A. So you would like to go to some suitable subset, which we call the Ziegler set, and check it there, right? So okay, so let's so some notation has to be introduced. Let me not get it wrong. So, right, okay. So we have the group. So we have the so A equals diagonal subgroup, that is the torus, maximal torus, split torus, diagonal subgroup, and I will look at A greater than 0. That will be as before, just like for the center, but now we are doing it with the diagonal group. You look at this one, right? So this, okay, and inside this we have A1. So the notations are not entirely consistent, but it's okay. So I have, which is A in A greater than 0, such that determinant A equals 1. Okay, so subgroup of the diagonal group with entries in this, so that the determinant is 1. And we also have A1 again it will be a subgroup of the ideal points of the diagonal group, which with entries, whose entries have absolute value. Okay. All right. And with this in mind, okay. So whatever. So by the way, you can reset now, and everything will be quite elementary for some time. Okay, so now we have the Iwasawa decomposition, right? Oh yeah, one more thing. Let me make one more subgroup here, which I call A of T. So we have this alpha I, which is basically the simple roots, right? So they go from A to GL1, right? And they are given by, if I have an element wherever, then alpha I of A goes to alpha I of A, is simply take AII and divide by AII plus 1. AI plus 1, I plus 1. Right? Okay. So we will define AT. This set will be an important set. This is going to be a subset of A1, so it's going to have determinant 1 and have entries in A cross greater than 0. Right? That will be A in A1 such that alpha I of A is greater than or equal to T for all 1 less than I less than n minus 1. So you have these, yeah? Absolutely. Yeah. Okay. So this set will be important for us. Essentially, when we're going to define Siegel sets now using them. So first of all, before anything else, remember we have the Iwasawa decomposition. That will also come in. Right? So what does that tell us? That says that GA equals NA AA and K, where that's a compact subgroup. And for G1, basically that's removing the Z greater than 0, so of course the NA stays where it is, but here we'll end up having A1, A lower 1 and A upper 1, but yeah, okay, let's do it like that, A lower 1, A upper 1 and K. Okay, so basically the diagonal, if you just remove the Z greater than 0, this is what you'll end up with. Okay, so now I can define a Siegel set as follows. So we take omega A to be a compact subset of NA, and we take omega A to be a compact subset of A1. Okay. And we will, and K is just K, we will take respectively elements, let's call this small omega A, small omega, this is N, small omega M, small omega A, and K. Okay. So if you have compact sets, then a Siegel set is simply a set of the following type. So let's just call let's index it by omega 8. How am I doing it? I forgot my notation. Yeah, T. This is going to be G in which is equal to omega n times A times omega A times K. So an element in G1, yeah, such that A is in 80. So what is 80? Point, right? So that's A is in 80. Okay. So okay. So this is what a Ziegler set is. Okay. It's called a Ziegler set. Any set of this form for a choice of compact omega A n, compact omega A, K and T is K is fixed and T is called a Ziegler set. Right? So it's very similar to a fundamental domain in that the GF translates of a Ziegler set will get you G1A if the Ziegler set is chosen properly. So that's the next point. Okay. So couple of remarks. So facts maybe which are not hard to prove. So the measure of a Ziegler set is always finite. That you can check. It will boil down to proving that the measure of AT is finite. Is always finite. So maybe one picture should be drawn. Projection of the Ziegler set onto the Archimedean part where f equals q, etc. and n equals 2, that is GL2. So then you are roughly looking at the usual picture for the fundamental domain of SL2R by SL2Z, but then you take this region. So this corresponds to, if you take t greater than √3 by 2, and if you take the coordinates in the upper half plane are absolute value less than or equal to half. Right? So this is what a typical Ziegler set looks like when you project to SL2R mod SO2. Okay? So this is what it looks like, and we're saying the measure of this set is finite, which is reasonable because you have dx dy by y square. So when you integrate, you get something finite. Okay. So
Ravi, with the G is product of 4 objects. K has only 3 objects, no?
sorry.
G, when we have written down the
No, there's A1 and here.
the next board, the first line of the next board.
Here, yeah, 1, 2, 3, 4.
What are the 4 elements?
1, 2, 3, 4. This is in G1.
So,
Nebula is the diagonal part.
So what part?
Nebula is the diagonal part.
Diagonal part. Yeah. So this is A1, right? So this is all things A1 here. Just the diagonal entries, but they have absolute value 1, right? Usual.
Basically, take care of the center.
AT is basically is more like the center, right? In some sense.
80 is
Huh?
go by the diagonal.
More like the diagonal, sorry.
so there is A lower one and A upper one.
A upper 1, and we are going to forget about A upper 1 for the most part anyway because we are going to take a compact set in that. So all our energy will be on A of t. Finally, so T is like this coordinate. T is like the y coordinate in the upper half plane picture.
Which is A lower one.
Sorry,
Which is A lower one.
A lower 1.
And A upper one.
A upper 1 is this. Entries have absolute value 1. Diagonal matrices with entries have absolute value 1.
Diagonal means scalar part.
No,
Diagonal.
diagonal. But if you're in GL2,
One of them is scalar matrices, the other is diagonal.
yeah, A lower one is AT, you see, is scalar, right? Basically, I mean, where is AT? Somewhere on the board. I've lost it. There it is. Not, see, it's in A1. Sorry, A1. Oh, okay. No, it's right. Okay, here it is. This is like
A lower one I follow. What is A upper one?
A upper one is just this. A lower one is this, right?
Yes.
It's all things in A greater than 0 such that determinant A equals 1, but A greater than 0 is just things in this, and things in this A cross greater than 0 are just things at the Archimedean places, right? And then the same entry in the Archimedean place. So this is a little more like the diagonal, not
Scalar
that.
matrix.
Yeah.
Diagonal.
No, but it's 1, 1, 1, 1 at the other places. No, in the Archimedean places it's like the diagonal.
Yeah, but it's a central.
Yeah.
It's a
Yes,
central element.
yes. Central. Okay, so Ziegler sets are finite measure, And the point is, if you choose them reasonably, then they are actually the translates of a Ziegel set give you everything. So you don't forget the other thing I wanted to say. Oh yeah, okay, so we can call it a theorem. Right? There is a Ziegel set. G such that, oh yeah, I have to stop here.
Well, that's an S.
Sorry?
That's an S.
That's an S, but I like to think of it as math frac.
S for Ziegel.
Yeah, S for Ziegel. So the Ziegel set is such that, such that
Max fact is not S.
Math practice.
no, math frac G looks not very different, but yeah, it's not the same. Yes. Yeah. Anyway, so so you have a Ziegel set S such that one. There is a Ziegel set such that one G1 is nothing but GF times S, right? And on the other hand, also 2, if you look at this set, XS, which is nothing but gamma in GF, so that two different translates intersect. This set is finite, right? So yeah, I'll stop here. It's not here what I'll get to, but in the next lecture, but I'll stop here anyway. Yes.